we could do it in this class, but it's up to you guys. Okay. Or maybe I will cover a little bit for you to get a feel. Okay, what it is. Okay, and we will go from there. Maybe. Okay. Anyway, so the first section is about eigenvalues and eigenvectors. So this is obviously a new thing, okay, which should be covered by like a high school. Okay. So eigenvalue and eigenvectors, they are very important concept in linear algebra. Okay, there are so many different applications for eigenvalues and eigenvectors, but in the class we are going to focus on the more like theoretical part. If you want to see applications, okay, I think the slides do not offer many application examples. If you want to know more about the applications of eigenvalue and eigenvectors, the textbook has many good examples, and I highly suggest that you know, after you learn the concept, you should check out those applications, because this concept is, they are just so important. Okay, they can be used across different research directions. Okay, so first, what is eigenvalue and eigenvector? Okay, if you have a square matrix, by the way, we discuss eigenvalue and eigenvector only for square matrix. Okay, we usually don't discuss eigenvalue, eigenvector for, you know, the matrix which has like different column and the rows. Okay, so if you know, your matrix, square matrix, okay, has a scalar lambda. Okay, that lambda, we call that lambda eigenvalue A. If there exists a non-zero vector x such that ax equal to lambda x, so you apply, you know, you just apply the A on your vector. Your vector, you know, gets, you know, either extended or shrink or keep it that way. But anyway, it's not vanishing. It's just like, you know, but it's either, it's going to result in a vector that is either the same direction or in the opposite direction of your vector x. Okay? If that's the case, okay, if that's the case, okay, we call this vector x as an eigenvector belonging to the eigenvalue lambda. Okay? And an important concept to let you know is, for one eigenvalue, you could end up with multiple eigenvectors. Okay? So the eigenspace corresponding to one eigenvalue lambda is the collection of all eigenvectors belonging to lambda and the zero vector. By the way, if lambda is an eigenvalue of matrix A, the eigenspace corresponding to lambda is a vector space, vector subspace. Can you show that? What is the definition of you know, the vector subspace. Do you guys still remember? There are a few things to check. First, it is non-zero. Okay, it's non-zero. Okay, so because when we say a value is an eigenvector, implicitly we already have a vector such that a x equal to lambda x, right? According to the definition. So that x belongs to this, by the way, that x is non-zero. Okay, belong to this, vector subspace. So this vector subspace is non-empty. That's the first thing. And then, if x is in this let's just call this eigenspace as a B, okay? If x is in B, we can show constant times x is also in B. Right? But this is easy, okay? X in B, that means a x equal to lambda x. Right? So cx, so a times cx. Because c is a scalar, so it's going to be c times ax. So it's going to be c times lambda x, or put it another way, lambda times cx. So obviously, cx satisfy this eigen, requirement of this eigen vector for lambda. Okay. The third one, if x, y in B, we need to show that x plus y in B. That's also a given. X, y in B, that means ax equal to lambda x. Ay, y in B, that means ay equal to lambda y. So x, y, a times x plus y. Okay, this can be decomposed into ax plus ay. So it's going to be lambda x plus lambda y. Or put it another way, it's going to be lambda times x plus y. So in other words, x plus y satisfy the requirement of this eigenspace. Okay, so obviously this eigenspace is a vector subspace. So how to calculate this stuff? Okay. Basically, okay, we do it from the definition, okay? Because if ax equals to lambda x, then we can move the lambda x from the right hand side to the left hand side. Okay, and we obtain this one. A minus lambda times identity matrix times x equal to 0. Okay, because we know x is a non-zero vector. So A minus lambda times identity matrix, its determinant must be 0, right? Or put it another way, it must be singular. Otherwise, we have no solution, right? We have no solution. So the determinant of this one will give us a polynomial of lambda. Okay, we call that particular polynomial the characteristic polynomial, or the matrix A. Okay, characteristic polynomial for matrix A. So, and the equation is determinant A minus lambda I equal to 0. It's called characteristic equation for characteristic polynomial, characteristic equation. Actually, you can use characteristic equation, characteristic polynomial interchangeably. Okay, I don't think that makes much difference anyway. Okay, so lambda. So basically, okay, you can solve this equation, okay, and you obtain those roots. Those roots will be your eigenvalue. Okay, and then you plug in those roots into here. Okay, A minus lambda I x equal to 0, and you will be able to obtain your eigenvectors that correspond to the eigenvalue lambda. Okay? So, few things to clarify. Okay, so obviously this characteristic polynomial. Okay, but for n by n matrix, you can imagine its degree is n, right? Before you do any calculation, you will be able to tell the degrees, and when you try to solve this n degree polynomial to get its roots, how many roots can you get? You'll say, oh, well, we will get like a couple. I mean, cannot be more than n. That's obvious, right? The roots, the number of roots cannot be more than n. That's obvious. But you may focus on the real roots, okay, meaning the roots that that are real numbers. But actually, okay, here, when you consider eigenvalue, okay, even the complex numbers can be eigenvalue. Okay, so in other words, your eigenvalue, if you have a degree n characteristic equation, okay, supposedly you should get n exactly n results for your eigenvalues. Of course, like some values could be repeated. Okay, 你可以有重根嘛， today, okay? But you get my idea. What I want to tell you is that, okay, the eigenvalues obviously